Lesson 3.3, complex numbers. You might see the term imaginary numbers. This is the square root of a negative number. So from here on out, the square root of -1 is going to be called I. Oh, and this is on page 149 in your book. So if you want to follow with your book, on page 149 here. Okay? And so square root of -1, we're going to call I. That's an imaginary number. I should write that down too. An imaginary number. Right. And complex number could have an imaginary component, but there could also be a real component, right? Like you might have like I plus 3 or something like that. Okay? Right. So now the funny thing about square roots and negatives is your calculator cannot actually solve that. You can try it out. So it'd be square root of -1 or square root of anything negative, and it says error, right? So you can try any calculator, maybe your own calculator. It's probably not going to give you an answer anything better than that. How about the square root of, oops, square that out. How about the square root of any other negative number, like -9? Does that have a square root? Well, not nothing that the calculator can do. Right? And if you think about this the other way around, like what's the opposite of a square root? It could be a square. So what if you square like any number? Let's say you square -3, for example. Okay, you see that comes out positive, right? And it doesn't matter what you square. The square of anything is always positive. Okay, so if you turn that around, see, you can only take the square roots of something that's positive in the first place, which would not be this. Okay? And so what we're going to do is call the square root of a negative value something that's called imaginary. Okay? Now, interestingly, that does have a practical application. And when we get to the text questions, there's anything related to alternating current. Yeah, so they have some electricity questions in here related to alternating current. There's a use for imaginary numbers. Right? There's some other uses too, but here, we'll read it later. All right, so we got I is going to be defined as the square root of -1. Okay. Here, I'm going to do an exercise with you guys to take you guys through like a pattern of i's. Right? Like, what if you square I? What if you put I to the power 3? What's I to the power 4? This will be useful later. Right? Well, if I itself is the square root of -1, I guess an imaginary number, if you square that, doesn't it just come out to -1? Okay, so that's interesting. So I squared actually is a real number. So this is imaginary. This is real. We're back to a real number again because -1, that's a real number. Okay? But what about I to the power of 3? Well, isn't that like, couldn't that be I times I squared? Right? And we know what I is, that's this. We know what I squared is, that's this. So I squared is -1, and I could just be I. So this is like negative I. Right? And then what's I to the power of 4? Well, couldn't that be like I squared times I squared? And I know I squared is -1. So what's -1 times -1? Well, that's just one. Hey, we're back to one, right? So this is actually a four-part pattern. Like anything I do beyond this, like what if I do I to the 5? Well, that's just I times I to the 4, but I to the 4 is just one. So we're back to just I. Right? Okay, so we're back to the beginning. Right? Okay, so if I did I to the 6, I to the 7, I to the 8, let's see, how would this play out? I to the 6, right? Well, that's like I to the 4, which itself is 1, and then you got I squared on top of that. So this is I squared, or -1. I to the 7 is going to be negative I to the 8 is I to the 4 times I to the 4, which is just 1 times 1, which is back to 1. Right? So you guys see this four-part pattern? Right? So when the powers are, they follow like this pattern of 4. Right? So if you had, here, let me make up a crazy one. What if I did I to the power of 73, right? Something like that. Right? Well, I know that's the same thing as I to the 72 times I to the 1. It could be like that, right? And I to the 72, well, 72 is a perfect multiple of 4. Right? So anything power of 4 is just 1. It shows up here, shows up here. Right? So this bit right here is just 1. So this is 1 times I, which is just I. Right? That's all. Right? So I to the 73 is I. Right? Same thing with, here, I'll do one. It turns out to be the same thing. What is I to the power of 101? Well, that's I to the power of 100 times I to the 1. I to the 100 is also 1. So 1 times I is, again, I. Something like that. Right? So you do powers of I now. Right? All right, so how about this? What now is the square root of -9? I tried that on my calculator earlier, just a few minutes ago. Okay? And remember what the calculator said. It wasn't able to find that. It says domain error. Okay, for when I type that in, that's what I get. Okay? But we can sort of pick this apart. We say, well, this is the same thing as the square root of -1 times 9. Like, well, that would be true, right? Oh, and I know what the square root of 9 is. That would just be 3. Maybe you can say plus or minus 3, right? And this square root of -1, now we're calling I. So maybe I could sort of call it like 3I. So I could do that. Like that. All right, so now we have a way to get square roots of negative numbers. Right? It'll be imaginary. Okay? And then the complex side of this could be okay, well, actually, I'll have shown you guys so far what's called pure imaginary numbers. Okay. But complex is if you add something to it, like, well, here, I think we'll run into some eventually. Okay. Like here, I'll give you guys an example. Like, what if I do 3 plus 5i, right? There's an imaginary part, imaginary, that's like the 5i, right? And 3 itself is real. Okay. So you could also graph this on a special plane that we haven't really done, although it may look kind of familiar. Okay. And that's real numbers versus imaginary numbers. Okay. So on the real axis, maybe I have 3, right? 3. And on imaginary, maybe like 5i is like up here. So that could show it sort of as a coordinate, right? Like 3, 5, like 3 plus 5i, you could graph like this. And guys, this is not an x-axis, y-axis. This is a real axis, imaginary axis, so it's a little different. I don't know if your book has you graph anything like that, but you might eventually see this at some point, right? There's fun stuff you can do with that too, right? So let's go back to the book then. Okay, so what did we do? Example right here, I think I missed this one. Square root of -294. Let's try this out. So square root of -294. Right. Well, 294, I do say that's an even number, so I can at least divide that by 2. I want to see like what are the factors of 294? Like break this down into its primes. Right? And this -1, I'll pull out, and I'll eventually call that I, but I wonder if this has some primes I can pull out. So 294 over 2, it's like 147. 7. Okay, guys, watch this. If you add the digits together, 7 plus 4 is 11, plus 1 is 12. That is a multiple of 3. So I know that this, anytime you add the digits together, it's multiple of 3. That means the number itself is a multiple of 3. So I can also take a 3 out. It's 49. Ah, I know what 49 is. It's 7 times 7. So I took out a 2, I took out a 3, and then 49 is 7 times 7, isn't it? Okay. Let me show you guys that this does multiply that. Okay. So I can do -1 times 2 times 3 times 7 times 7. Right, it should tell me -249. Let's see if it does. Okay. Uh, sorry, 294. That's what I meant. -294. Yeah, it sure is. Right, it matches. Right, so that looks like this. So what can I do? Okay. Well, the 2 and the 3 are stuck underneath the radical because those are prime numbers. So you just stuck right. But the 7 times 7, which is 49, that does have a perfect square root, which is 7. Anytime you have a pair of numbers right underneath the root, you can pull that number out in front. So I can pull a 7 out. Right? This -1 square root right, becomes I, so it'd be like I. Right? And I still have a square root, so multiply by and 2 times 3, which is 6, and that's just left in there. Right? So I'm pretty sure the book wrote the answer like this because I checked ahead of time is they put it in this format. They got the real number, imaginary number, and whatever's left, they left under the radical. So let's see if that's what they wrote here. Yeah, okay, that's exactly the format they also have. Right. So the 7 first, and then the I, and then the square root of 6. Right. So as you guys are typing the numbers into Alex, they might want that order maybe, or I don't know, or maybe they let you multiply in different orders. Maybe you guys can try it out and see what. Right. So what else we got? Example 2, products of pure imaginary numbers. Right, so we got square root of -10 times the square root of -15. Right? Well, similar idea. I know that I can break these down into primes. Maybe I can sort of think of it that way. Right? So square root and negative, I'll pull that out. 10 is the same thing as 2 times 5. Right? And that might be useful because I could combine it with some primes from this one. So I got another square root. I got another -1, and then no, 15 is 3 times 5. Isn't that true? So now I can put this all together. So I can say it's giant square root. I got a -1, -1, right? Or if I like, could I pull that out as I times I? I'll just go and do that, which is I squared. Right? And then under here I got this 2, I got this 3, I got this 5 and this 5. Hey, look at that. There's a pair of numbers here and it's root, so I can pull that out. So 5 times 5 is 25, but the square root, that's just 5. So that's 5. Okay. I got an I squared, and then I got a square root of 2 times 3 is 6 again. Okay. But you guys know what? One more thing. You guys remember I told you guys that there's that four-part pattern. You guys remember this? Okay. So if I is the root of -1, I squared is -1. Right? And then, so I is the square root of -1, I squared is -1, right? And then it follows this four-part pattern. By the time you get to I to the fifth, you're back to I again, right? And so this I squared right here is -1. So the whole thing should be negative. I got a 5. I got a square root of 6. I'm pretty sure that should be the answer. Okay, let's check and see if that's also what the book says. Okay, -5 root 6. Um, yeah, that's it. -5 root 6. Same thing. Okay. All right, example 3. Equation with pure imaginary solutions. Okay, so they start you off with, so it's example 3. X squared plus 81 equals 0. Okay. Well, if you're just following your normal algebra rules and solving for x, okay, now you might have a hunch, well, hey, I wonder if I could sort of factor this. But to try to factor this and might unfoil it, you can't do that with real solutions when there's a plus here. Now, if it said minus, you do, oh, x plus 9, x minus 9. Okay. Maybe I'll round back to that and talk about that later. But you could also think of it this way. X squared equals, you could subtract off the 81 like this. Okay. And then take the square root of both sides. So x equals the square root of -81. Okay. Right. Now the square root of 81 would be 9, and the square root of -1 is I. So I think this should be um, uh, okay, 9 and then I. They should look like that. You know what? Now that I'm thinking of it, I wonder if this is plus or minus. Because I would get that by factoring also. Okay. I think this is plus or minus. Let's see what the book says. Yeah, in fact, they did include the plus or minus here. They sure did. They sure did. Right? Because I guess we're taking the square root ourselves. And so by doing that, there would be a plus or minus. Okay. Now, you could have, instead of gone through this approach, right, like this set of steps, you could have from the beginning factored this. So I'm going to say factor. Now, this factor is a little bit funny though, because, okay, so something like this, right, is equal to 0. Okay. It's kind of like reverse FOIL. I'll write the term FOIL, although FOIL is going backwards. Okay. So there'd be an X and an X, and then two numbers that, say, you multiply to 81. So you might think, okay, couldn't that be like 9 and 9? Okay. Right. So let's say you started with that. Let's say you did like plus 9 and here. Let me say, um, well, how about this? Okay. If you do plus 9, you get the x squared, that's good. You get the 81 for the last terms, that's good. But the inside-outside terms would be 9x plus 9x, which gives you an 18x. I don't see anything about an 18x for that outside-inside, so it couldn't be plus 9 plus 9. That wouldn't work. But, well, maybe it's plus 9 minus 9. Try that. Maybe FOIL that to check your answer. So first, x squared, good. Right. 9x and -9x cancel. Great, I don't see next terms, so that's good. But the last term is 9 times -9. Well, that's -81, not positive 81. So this doesn't actually work, right? But maybe you could, since you know what the answer is anyway, set this. Right? This is actually 9i, -9i. This will actually work. I think they call it the conjugate pair, or some version of that. Might show up later. Or like a complex conjugate. Right? If you FOIL this out, it actually does bring you back to the original. Watch this. X times x is x squared, so that's good. Outside and inside just cancel out, so that's great. Right? Now, if you have, here, I'll write this part out. 9i times -9i. I'll show you guys it does in fact multiply to positive 81. So 9 times -9 is -81. And then I times I is I squared. But I squared is -1. So it's -81, which is, in fact, 81, which matches the original. So yeah, we're definitely good. Okay. So this is a factor form. Now, the factor form, remember, this whole thing is equal to 0. This bit could be 0, or this bit could be 0 to 0 the whole thing out. Either way, it leads you back to the same solution we got with this other method from before. So there's two different methods that lead to the same answer. So x is plus or minus 9i to satisfy the original statement. couple ways to do that. Algebra method, factoring method. All right. So okay, now we move on to what they're officially calling complex numbers, which is kind of the title of this chapter. Okay. But that's if you have a real number plus an imaginary number. I think I showed you guys an example earlier. Okay. So here we go. Okay. So example four, let's just jump straight to that. Quite complex numbers. Find the x and y. Oh, interesting. They're having you solve this right away. Okay, we'll run with it. Oh, and here we go. I almost skipped over this part. A plus bi and a minus bi. Yeah, they're calling that complex conjugates. Right, that's what I mentioned before. I said that these two pieces right here could be complex conjugates of each other. Right, like something like that. Which I bet that's going to be useful down the line. But find out. Right, so let's go ahead and solve this example. Okay, see if we can do that. I got 5x minus 7 plus, and then y plus 4 all times I equals 13 plus 11I. Find values of x and y that make the statement true. Oh, okay. Actually, this isn't nearly as hard as I. Okay, so this won't be bad. What you have to do is um, put all the real numbers together, put all the imaginary numbers together, and then be able to equate it that way. So here, I'll rewrite this. I'll just strip this out. 5x minus 7 plus, can I distribute this I? Make it I times y plus 4I equals 13 plus 11I, basically like that. Right. All right, now there are real parts and there are imaginary parts. If I circle the imaginary parts, right, those two have to equate. Actually, I overcomplicated this, didn't I? I should have left the original statement. Um, let me go ahead and do that. Let me backtrack a little bit. Backtrack. You could have done that, but it's not very helpful. Okay. Okay. Actually, if I just focus on the I bits, just the imaginary bits, if these two have to be equal to each other, I can solve for y by doing this. Okay. You guys think that y plus 4 has to be equal to 11, right? Because if I tag on the i's, the only way for it to equate in the imaginary part of this complex number is for this part to be true. So subtract over 4, y must be equal to 7. Okay, so that's one of your values, by 7. Now the x bits are the real part. Here, maybe I'll circle those in pink. Maybe those stand out in pink. Right, so this pink part here has to be equal to this pink part right here, right? Because that's the real part of this complex number. So complex is real plus imaginary. So now I can handle that. So the 5x minus 7 must be equal to this 13 right here. Okay? So add over 7 plus 7 plus 7. 5x is 20. Divide by 5. X is equal to 4. Right? So I think that's your solution right there. X is 4 and y is 7. Right? Double check the text. Okay, well, they walk through a process here. I have to check my teacher's manual off screen here. This is example 4 on 151. I flip over here. Example 4 on 151. We got, where is it? Yeah. They got x4 and y7. Okay, that's exactly what they got. I'm looking at it off screen. Okay, so that's the answer right there. Okay, so the real matches the real, the imaginary matches the imaginary, and then you can solve for x and y. Okay. All right, so that's all right. Okay, example 5, add or subtract complex numbers. So I think this is pretty similar to what we just did, that the real numbers would add together and the complex numbers could add together, right, separately from each other. So 8 plus 3i minus, and then in parentheses, 4 minus 10i. Okay. Well, first thing I'm going to do is distribute this negative right here. So I'll make that 8 plus 3i minus 4, and then minus this brings me back to plus 10i right here. Okay. Now I see these two real numbers, these two imaginary numbers. So let's add the reals together. So 8 minus 4 gives me 4. And 3i plus 10i is 13i. Okay. So that looks like a complex number, right? Real plus imaginary. Okay, so that's example 5. We check the book, make sure that's what we got. Example 5. 4 plus 13i. Yeah, 14. 4 plus 13i. That's the answer. Okay, number 6. Multiply complex numbers. Ooh. Oh, and look, we're at this alternating current example. Okay. So we're doing some electrical engineering here about alternating current. Okay? Here, quick physics connection here. So if you plug a battery into an appliance, here I got one right here. Okay, don't want to take this out because it's my screen remote. Okay, you see these AA batteries. This is called direct current. So there's a a cathode and an anode, and it's making a complete circuit in here, and it's allowing me to control the projector. Right, so this is called direct current. And the same thing if you have a wristwatch, if you have a little batteries inside your calculator, right, that's all direct current. But if you plug something into a wall outlet, it's actually a different kind of electricity. Okay? It's called alternating current. Okay? And you can transmit electricity across a whole power grid more efficiently that way. And electrical engineers who are working with whole power grids, well, there's actually a real application of imaginary numbers as it applies to electricity. So they give you this equation here. Now, from a physics point of view, this looks kind of funny, but we'll just run with their notation. They're calling V equal to voltage. They're calling C current. In physics, we usually use I, but let's just stick with what says C is current. And they're using I for something they call impedance. Impedance. Now, I know in direct current circuits, we use R for resistance, is what we call it. Here, calling impedance. That's up a little bit. Right. So if the current is, so they give you this 3 plus 2J amps. Now, in this case, J is the imaginary number, so we'll treat this as imaginary. Okay? And they're given the impedance as 7 minus 5J ohms. So this is amps, like amperes, and this is ohms. So those are like physics units. Okay? Then what is the voltage? Well, the voltage, they tell you, is just the current times the impedance, right? In physics, I call that Ohm's law, right? So Ohm's law, here, I'll spell that out because you guys want to look that up, Ohm's law, so physics term, right? And so the math application is we get to multiply these two together. Look at that. There's your C, there's your I, right? And maybe later on, like if they give you the voltage and they either ask for the current or the impedance, maybe you could sort of divide these, right? Oh yeah, I think that's the next example, right? It's coming up. So we're going to multiply. We're going to say the voltage is equal to current times impedance. The current is 3 plus 2J. Remember, J is the square root of -1. So imaginary makes it imaginary. And then the impedance is 7 minus 5J. Okay, so this is amps, this is ohms. Okay. Well, I can FOIL. So I'm going to write down FOIL. So that's first, outside, inside, last, right? And that'll lead us straight to the answer, or should. Let's see. So the voltage would be 3 times 7 is 21. Okay, outside, negative 15J. And then inside is plus 14J. And then last is negative 10J squared. Okay. I think we can clean this up. So we got 21. Now these two middle terms, negative 15 plus 14, simply becomes negative 1J. Okay? And then minus 10. Now remember, if J is the square root of -1, and you square that, doesn't that just become -1 again? Think we go way back a minute. Right? That's this four-part pattern, right? Or powers of I. Isn't that four-part pattern? Right? That's what this is right here. J squared is -1. So negative 1, doesn't that just become plus 10? Right? And this is, so now we're back to a real number. It's real again. Yay! This 10 plus this 21, that makes like 31. So the voltage then is 31 minus J. This could be called volts. Right? How many volts? I think that's what we're looking for right there. Right? 31 minus J. See, is that... Well, they say something minus J. That is 31 here. I'll check my teacher's manual off the screen. This is page 152. Right, that's example number 6. Yeah, that's exactly what they're saying it is. Right, 31 minus J volts. Right, so we're good. Okay, one more example. Can you divide complex numbers? Let's see. So I got 5i all divided by 3 plus 2i. Right? Now I got this I and this I. I bet what they're looking for is to not have imaginaries in the denominator. Like maybe this is perfectly fine, like as a physics answer, but maybe we could sort of like rewrite this or rethink this. You get all the i's in the numerator as a matter of convention. Right? That's usually what they want you to do. And the way to do that is, do you guys remember back a page, this complex conjugate, a plus bi and a minus bi are complex conjugate? I think we could take advantage of that to get the i's out of the denominator. And the way we'll do that is we'll multiply the complex conjugate in here, right? So I can get rid of the imaginaries in the denominator by multiplying 3 minus 2i, right? Okay. So this will eliminate the i's in the denominator, but see, I can't just make this up out of the air. If I also multiply the numerator by 3 minus 2i, watch the theory of why this works. Guys, what is this fraction right here equal to? Well, it's equal to 1, right? When the numerator and denominator match. So you're effectively multiplying by 1, right? Here's that times 1, which means you're not really changing it. You're just manipulating it so that the fraction looks a little different, right? Okay, so this is a completely illegal move mathematically. Okay, so I can work with this. What I'm going to do is distribute this 5i to both this 3 and also this negative 2i. Okay? And then the denominator, I will FOIL that out. Okay, so big old fraction here. So I got 5i, here, I'll make this really clear, times 3. Then, well, I got a negative, so I'll go ahead and pull that out here. Okay, 5i times 2i. Okay, so like that. Okay, okay, so I took care of the negative right here. Sorry. And then in the denominator, I'm gonna F-O-I-L. Boil this out. I'll spell that out. F-O-I-L. So first, 3 times 3 is 9. Outside, got minus 6i. Inside, plus 6i. Ah, I see why we're using that complex conjugate, because that just got rid of the i's. And then minus 4i squared. Okay? 2 times 2 is 4. Minus plus makes a minus. We got I squared. Okay, so make sure that makes sense. Okay, and then we can clean this up from here. So the fraction, 5i times 3, that sounds like 15i. And then minus 5 times 2 is 10i squared. Okay. In the denominator, I have 9. These two cancel. Minus 4i squared. But don't forget, I squared is negative 1. Because remember, I itself is the root of negative 1. Right, so these two go hand in hand. Right? So I can replace, switch over to peaking for a moment, this with negative 1. And this also with negative 1. Right? So that would turn these numbers back real again. Ooh, back real. So here, I think I can fit this. It is. Got enough paper. 15i, right? Now, 10 times negative 1 is negative 10. I'm subtracting that off, so it's plus 10. Brings back plus 10. And then down here, I got 9, and then minus 4 times negative 1, so that's plus 4. Okay. Actually, one more step. I'll combine these two and make 13. So that's 15i plus 10, all collectively divided by 13. Okay. That should be the answer right there. Okay. All right, let me check my teacher's manual, make sure that that is in fact the answer. So example 7, we got 15. Okay. The only thing they did is they split this into two separate fractions. So they did 15i over 13 plus 10 over 13, right? Or you could just leave it like this, right? Either way, right? Or you can put the I after. So there's a few different ways to write this, but that's the answer. That's the correct answer. Here, I'll write it some other ways. So you could go, let's continue it right here. Right. So you could also write this as 10 plus 15i, all collectively divided by 13, right? Or you could split this into separate fractions. You say 10 over 13, that's the real component, plus 15 over 13i, right? So this, and this are all the same thing. And so all three of those could be valid. So let's go on to some text puzzles. Right, so highlight quite a few because I might be able to do these fairly quickly. Right? And they check ahead of time to see if some that were slightly different versions or a little bit different answers. So let's start with square root of negative 72. Right? Well, let's see. Got square root, got negative 72. Could that be 9 times 8? 9 times 8. Okay. And that further breaks down into 9 is 3 times 3. 8 is 2 to the power of 3, which is 2 times 2 times 2. Okay, yeah, and this is all square root. Right? All right, now let's pull some stuff out of the square root. So I know the square root of -1, I can pull an I out. So I, okay. 3 times 3, square root is just 3. So that pair of 3's pulls out. Right, this pair of 2's also pulls out. So I can pull out a 2. Now I am left with this 2 underneath the radicals, so that's just stuck right there. Okay. All right, last, to clean this up, 3 times 2 is 6. And then as a matter of format, see your book, put the 6 in front, followed by the I, and followed by whatever's left in the radical. Right, so I'll write it that way too. Okay, in case Alex is possibly thinking about what order you put everything in. Right, so the shade answer right there. Right. Number 6. Square root of -99. Well, I know square root negative um, 99 is like 9 times 11. Okay. And if you want one more step, I'll do 3 times 3. Okay. And then, anyway, I can pull that out, and that is 3. Okay. This negative pulls out as an I, so I got a 3. I got an I, and I got a square root of the 11 is second, because 11 is prime, so I can't really do anything with that. Right, so that's number 6. Boom. Okay. Number 8, the Ocho. Square root -6 times square root -3. Ooh, well, here. So I can pull an I out here and an I out here. So I got an I, and then here's 6 all turned into 2 times 3. And I got another I from here, and I got the square root of 3. Okay. Now look at this. I got square root of 3 and square root of 3. So those two combined to just make a regular 3. Okay. And ooh, what is I times I? Ooh, well, that would be I squared. And you guys remember, if I is the square root of -1, then I squared is 1. Or sorry, -1. That's what I meant. Right there, it's a 4, 2, right? Yeah, there's good. -1. So this just makes negative. 3 and 3 makes 3 because square root pulls out of the root. And then there's one number I have that's stuck into the square root, and that's this 2. So that's the answer to number 8. Okay. So go through that again. 6 is 3 times 2. Combine it with this 3. Pull the 3 out. -1, -1. Square root squared. 3's out. Negative. Okay. And then still got a 2 seconds. Okay, number 10. I got, ooh, now they're giving us I's. I got a 3i. I got a -2i. And I got a 5i. Okay. So I'll pull the negative out in front. I got a 3 times 2 is 6 times 5 would be 30. That's 30. And then I have 3 i's that are all multiplied, so that's like I to the power of 3. Okay. Well, let's go through that pattern. So if I is the root -1, I squared is like -1. I to the 3 is like these two multiplied together, which is -I, isn't it? Right? That's what this is right here. This is this. So this is -I. Well, all right, so here, keep track then. Got that negative. I got a 30. And then I have -I. Well, now these two negatives combine. And what's negative times negative? A positive. So it just goes away. The answer is 30i. Okay. That's it. So this is this. It's the same thing. Same thing. There you go. All right, number 11. Oh, actually, I think I can do that right down here. Okay. So number 11 says, what is I to the power of 11? Okay. Well, I did a crazy one with you guys earlier, and it was based on this 4-part pattern. Because by the time you get I to the 4, that's I squared, which is back to +1. Okay. So here's your 4-part pattern. Okay. And anything beyond that, it just repeats. So I 5 through 8, I 9 through 12. Right. So every time you hit a power of 4, it just goes back to 1 again. Okay. Here, I'll expand this out. So in case you're not seeing it, it's not clicking, then this is like I to the 4 times I to the 4. So that's like 8 i's, but you kind of get up to 11. So there's 3 left over. Isn't that the same thing? Okay. But I to the 4 is just +1. That's right there is 1. And this right here, that's also 1. Yeah. So it's just 1 times 1 times I to the 3rd. And I to the 3rd, that's is -I. So that's 1, times 1 times negative I. So the whole thing is just negative I. That's it. That's the answer. Okay. So if you have crazy powers of I, what I would do is say, well, in terms of like multiples of 4, what is that? Here, I'll make up my own. Let's do a real crazy one. What if you have I to the power of 1,024? 24 like that. Okay. Well, 1,024 is a multiple of 4. Okay? If you want to know something multiple of 4, really all you need is the last two digits. 24 is multiple of 4. Therefore, anything in front of it. Okay? This is just one. That's all. That's the whole thing. Okay, that's it. Boom, done. 17. 17. Solve each equation. So 5x squared plus 125 equals 0, right? There might be a couple of different ways you can do this. One way is say I could subtract over 5x squared is negative 125. I could divide both sides by 5, right? Over 5 over 5. Maybe I could have done it to start with. I could factor that out, however you think about it. X squared equals negative 25, right? So then x is the square root of negative 25. Okay. Now, the square root of 25 is 5, but there's also this negative. So, oh, and don't forget the plus or minus. So we're going to introduce a plus or minus. Okay. I need to pull an I out. Well, actually, the rest is just 5. Yeah. Here, I'm going to rewrite that. X equals plus or minus 5i. I think that looks a little prettier right there. So, go for that right there. There you go. That's it. Plus or minus 5i. You could have factored from the beginning. So here, I'll do this a different way. What if I do this as pull out 5, and I have x squared plus 25 equals 0. Okay. Then that's equal to, okay, keep that 5. I could do x plus 5i, x minus 5i, and it's equal to 0. So what would 0 is swapping out? That's if this bit is 0 or if this bit is 0. And then that leads you back to, yeah, the same thing. X to be plus or minus 5i would also work that way. So this is like a factor way to do it. So I did traditional algebra, got this. Or if you factor it, it's a little bit different path, but it leads you to the exact same answer, plus or minus 5i. However you get it. All right, so 17. All right, next. 19. Determine the values of x and y that make each equation true. Yeah, saw some like this earlier. 9 plus 12i equals 3x plus 4yi. Okay. So the reals have to match the reals and the imaginaries have to match the imaginaries. Okay, so this is real and this is real. This is imaginary. Well, imaginary shortened. Okay, and this is also imaginary. Okay, so the real has to match the real, the imaginary has to match the imaginary. Yeah, let's put it together. That means that 9 must be equal to 3x. Divide both sides by 3. X equals 3. Okay. And over here, I've got 12i equals 4yi. Okay. So this 12 must be 4y. 12 equals, let's get an I here. Whoops, didn't mean it right over there. 4y. So divide both sides by 4. Ooh, y is also 3. Interesting. They're both equal to 3. Right? I think I did that right. Okay. 25. Simplify. So 25. Here. You got 6 plus I plus, and then 4 minus 5i. Things like that, right? Something like that. Okay. So combine the reals. 6 and 4 is 10. Combine the imaginaries. I minus 5i. That's like minus 4i. That's it. That's the whole thing. 10 minus 4i. Okay, next. 30. Oh, electricity. Electricity. Number 34. 34. Electricity. Okay. So use the formula. Remember, this is Ohm's law. So we're calling V voltage. C we're using for current in this book. If you're in my physics class, we use a different character. And I, they're calling it impedance. Right. And it's all connected by Ohm's law. V equals CI in this case. Right. And if this is alternating current, then you get to bring in imaginary units. So the current is 3 minus j. Remember, j is our imaginary number. Okay? And then the impedance I is 3 plus 2j. Okay. So this would be amps. This would be ohms. Okay. So this is all given right here, given that. So find the voltage, right? Yeah, find the voltage. Okay. All right, so let's just plug this right into Ohm's law right here. And so here's our guiding formula, Ohm's law. So V equals CI. So V equals, now C is 3 minus J times, and then I is 3 plus 2J. Okay. So let's do some FOIL, FOIL. Got first, outside, inside, last, FOIL, FOIL. So 3 times 3 is 9. Minus, or sorry, what is that? Plus 6j. 3 times 2 is plus 6j. Then minus 3j here. Then minus 2j squared. Right? That big? But j squared, you guys know, is equal to -1. Right? So, here, I'll throw in an extra line. So v equals 9 plus 6j minus 3j, then minus 2 times -1, the negatives go away, and it's plus 2. It's the same thing as plus 2. Okay? And last step is going to go voltage equals, I can combine the real numbers, and I can combine the imaginary numbers. So 9 plus 2 gives me 11, and 6j minus 3j is 3j. Okay, so that should be the answer right there. Okay, that would be so many volts. Okay, so many volts. Okay. There's a real component to the voltage. There's also an imaginary component, and for alternating current is what apply to. All right, 35. Simplify. 35. So we got 5 divided by 3 plus I, right? Again, maybe as a standard, I want all the imaginaries to show up in the numerator, not the denominator. So I'm going to bring in a complex conjugate, which I think would be 3 minus I. But remember, I have to multiply top and bottom by that same complex conjugate. Because remember the theory of how this works. Right? This whole fraction is equal to 1, so I'm technically multiplying by 1. Right? So I'm not really changing the original statement. Right? What I am doing is I'm manipulating it so that I can get all the imaginaries only in the numerator. So the denominator, I do have to FOIL, F-O-I-L. So F-O-I-L. First, outside, inside, last. Okay? And the numerator can more simply classical distribution. So 5 times 3 is 15 minus 5i in the numerator. And denominator, so you got 9 minus 3i plus 3i. That's the purpose of doing this method. And then minus I squared. But remember, I is root -1, therefore I squared is -1. Okay, so this bit right here is -1. So that's 15 minus 5i, all divided by 9 minus -1 is 9 plus 1. So that's like 10, isn't it? So that's 15 minus 5i, all divided by 10. Oh, you know what? I can actually do one more step because these three numbers are all multiples of 5. So I can pull out 5 over 5, right? Right. And then reduce it that way. So it'd be 3 minus I, all divided by 2, like that. Right. Here, just to clean that up a little bit, I got an extra paper over here anyway. And spell it. Right. Right. So the answer could be 3 minus I divided by 2. That's probably perfectly fine itself. Right. If I want to split this up into separate fractions, this could be equal to 3 over 2, and then minus 1/2 I. Right. That's the same thing. Right, so this and this and this, no, it's all the same thing. Right, split that up. All right, that was 35. All right, let's do 37. Okay, so it's just like a similar concept here. Yeah, 37. Okay. So you got 6 minus 5i all divided by 3i. Okay. How about this? If you like, could you think of this here? I'll put this in pinky if you want to. If maybe this is helpful, maybe not. Can you think of this as like 3i plus 0? Right, please something. Right. Or 0 plus 3i. Maybe I should do it that way. Here. Yeah. The complex conjugate is going to be negative 3i. Here, I'm gonna start here, just to write it the way I want to write it. 6 minus 5i over 3i. Okay. And the 3i is really 0 plus 3i, if I want to think of it that way. So the complex conjugate is going to be 0 minus 3i. Or if you like, just negative 3i. Okay? You could have just jumped straight to that. You don't have to actually write the 0, right? But if it helps, if you say, oh yeah, I do see how it's actually part of a larger complex number, right? Then maybe that helps, right? So however you think of it, or you could just ignore the 0, whatever. Okay? So I can distribute this now negative 3i into each of these terms over here, and then multiply this out in the bottom. So in the top, say it's 606 negative 18. I have an I now. And then minus minus gives me plus. 5 times 3 is 15. And that's I squared. Remember, I squared is negative 1. So that could be helpful right there. But not finished yet. So about the denominator. That's negative 9i squared. Okay, this also shows up right there. Right, so got negatives flying all over the place. Okay. So it's negative 18i. This is minus 15. This all divided by, well, negative 9 times negative 1 is positive 9. Okay. And finally, I can clean it up like this. I got somehow got the imaginary over here and the real over here, I think, because just how this started out. Okay. Here, finish off in this corner of the paper right here. So negative 15 over 9, and then minus 18i over 9. Like if I split it up into fractions, right? Actually, both of these can be reduced because 15 is a multiple of 3, 9 is a multiple of 3. So take out 3 over 3, is that like 5 over 3? So that's negative 5 over 3 minus, right? And then 18 over 9 is 2, so it's like 2i. Okay. So I think this would be one way you could write the answer. Something like that. Yeah, that should work. Okay, looks good. Right. Yeah, okay. Again, the goal was to get all the i's out of the denominator, and yeah, we've done that. Right. So there is I, but it's now in the numerator. Ooh, yeah, that's good. Right. That was 37. And we are looking here. Uh, okay, so I highlighted just 3 more. So I'll do 3 more with the guys here. Got 40, 44, 46. Okay. So number 40. I got 2 minus I root 3 over 2 plus I root 3. Now that's interesting that the numerator and denominator are conjugate pairs of each other. Wonder if this is going to come out with something interesting. Right, well, we'll find out. Let's play it out, see what happens. So the conjugate pair of this denominator is 2 minus I root 3. So put that in the denominator, but also the numerator to balance this out. So we've done a few of these, right? These complex conjugate. I'll spell that out in case you see that term again. Complex conjugate. It's like conjugate with the eyes, like just like that. Okay? And this is set up in such a way that when I FOIL out the denominator, FOIL, first outside, inside, last, it should get rid of the eyes. Now the numerator, I also have to FOIL FOIL. Right? So we'll FOIL the numerator and the denominator, make a big old fraction here and see what happens. So 2 times 2 is 4. Then outside 2i root 3, and it's minus, so minus 2i root 3. Then inside 2i root 3, so that's another minus 2i root 3. And then Okay, minus minus makes plus. We got an I squared, and root 3 times root 3 is 3. Okay, like that. How about denominator? 2 times 2 is 4. Then outside, inside are going to cancel out, right? Because that's the purpose of this method and how you set it up that way. Okay. So, yeah, outside, inside, whatever. And then last, I got a minus. I got an I squared, and then root 3 is 3. So look at that. Okay. Okay, I can definitely clean this up. So what I'm going to do here. Okay, well, I know this I squared is equal to -1. So I can pop that in there. Okay. Um, how about this? Guys, this is 4. This is -3, isn't it? Isn't this whole bit right here equal to -3 equals -3? Okay. So what's 4 minus 3? Well, that's 1. So I get a 1 up here. I think it's everything real I have left in the numerator. Okay. And then 2i root 3, 2i root 3, they both subtracted. That's like minus 4i root 3, right? And then down here, oh, look at this. This I squared is also -1. So this is -1. Okay. So if that's -1 equals -1, this whole bit right here is also -3. Right? But this time it's being subtracted. See, and the top was being added and being plus -3. Here we're doing minus -3, right? Which is the same thing as plus 3. So this is really 4 plus 3, which is 7. So the whole denominator is 7. And the whole purpose of this process is to get the imaginaries out of the denominator, which we've done. Okay? So I bet this would be a perfectly valid answer right here. Right here. Okay? If you wanted to split that up into two separate fractions, you could also do that. I'll write it that way too, just in case you want to see it that way. So this is the same thing as 1/7 minus 4i root 3 over 7. Okay, so this and this are the same thing. Right? If you want to write it this way, if you want to write it this way, we both get you there. Okay. That's 40. Right, let's check out 44. Okay. These last two are both alternating current electricity examples. So number 44. The voltage is 24 minus 8J volts, and the impedance is 4 minus 2J ohms. What's the current? Okay. So remember Ohm's law, voltage equals current times impedance. Okay. So if we're solving for the current, I think therefore current is equal to voltage divided by um, impedance, right? Wouldn't it be? Okay. So voltage divided by impedance. So the current, let's go ahead and spell it out, current equals this voltage divided by this impedance. Okay? And then let's do that process with the complex conjugate. Here, we're going to rotate this a little bit, get out of Ohm's law. Way, right? Out of the way. Complex conjugate to get the imaginaries out of the denominator. So like 4 plus 2j, 4 plus 2j. Right, we've done a few of these. Right, and then, okay, I have to do a bunch of foiling here, a bunch of foiling. So that's F, O, I, L. And down here it goes F, O, I, L. So it'll be foil, foil. Okay, so the current equals, right? 24 times 4, I think it's 96, right? 96, and then plus 48J minus 32J, and then minus 16J squared, where J squared is -1. I'll keep that in mind. So that's kind of eventually it's up there. And the denominator, 4 by 4 is 16. And then the outside inside cancels out. That's why I set it up this way. And then last is minus 2 times 2 is 4, J squared. Again, this J squared is -1. Okay. So the current equals, okay, clean this up. Well, 96 minus 16 times negative 1, same thing as plus 16. So that's 112. 48 minus 32 is like minus 16j. And then down here, this is negative 1. That makes this plus 4. This whole thing would be plus 4. 60 plus 4 is 20. Well, it'd be this many amps. How many amps right there? Actually, I could reduce that because I see those are all those numbers are multiples of 4, aren't they? Almost 4. So actually, maybe I'm not quite done yet. Okay, so let's pull a 4 out of that whole thing. So 4 out of 4, and then what's 112 over 4? That's like 28 minus 4j. And this would be all divided by 5. So, okay. Okay. So this should be a reduced form. That looks a little better. Okay. And then if you wanted to, you could again split this up into two fractions. So this is the same thing as 28 over 5 minus 4j over 5. Yeah, so many amps. So my unit is amps. Amperes. All right, there you go. So either one of these is an okay final form. All right, and last one that I'm doing with you guys is 46, also electrical engineering. The 46. The standard electrical voltage in Europe is 220 volts. So let's say voltage is 220, that's volts. Okay. Find the impedance if the current is this many amps. I'll just do one of these with you guys, because we've done quite a few of these. Right, so this has an A, B, and C. Just like, find those with us, find those with us. So it's really like three questions. So I'll just do 46A with you guys. So 46A. So it says if the current is 22 minus 11J amps, amps. Okay. Find the impedance. So I can say voltage equals current times impedance. This is Ohm's law. Okay. Therefore, impedance is voltage divided by current. Okay, so we'll use this right here. Okay, so impedance, I'll spell it impedance, A and C, equals voltage over current. So that's 220 volts over 22 minus 11J amps. Okay. There. Okay. So that could get us the impedance. Now I'm going to multiply by a complex conjugate here. Oops, I should have left a little space. Complex conjugate is going to go 22 plus 11J. But remember, do that top and bottom so that it balances out. Right? And then we'll do a bunch of foiling. F, O, I, L. Actually, the top is more of just a standard distribution. Point, point. Right, so we'll do that. Okay. Right, so impedance equals, so what's 220 times 22? That's like 4,840. And then if I just did times 11, that's plus 2420J. So that. Now the denominator, 22 squared is 484. The outside and the inside cancel out because it's set up that way. 22 times 11J minus 22 11J. And then finally, minus 11 squared is 121. J squared. But remember, this J squared itself is negative 1. So I'm thinking this little cloud bubble here. Right? That is that. Okay. So I'm subtracting negative 121 times negative 1. That's the same thing as adding 121. So 484 plus 121, that's like 605. So impedance is, okay, keep my 4840. This should be some number of ohms, right? Plus 2420J, all divided by 605. Yeah. Okay. So I think, you know what? I'm saying the same thing. all three of these numbers are perfect multiples of 5 for sure, because they end in a 5 or 0. So I can reduce that. Here, I'll go ahead and do some reducing here. Okay, let's reduce this thing. I'll pull out a 5 over 5. So impedance equals pull out a 5 over 5, so it cancels. Okay. What is 4840 over 5? That's like 968 plus what's 2420 over 5? That's 484J. And then what's 605 over 5? It's like 121. Okay. Now I know 121 is 11 squared. Okay. So this is 11 times 11. Um, if 11 does not go evenly into either one of these, then that means I'm done reducing. So can I divide 968 by 11? Oh, actually, I can. Oh, that's interesting. I wasn't really expecting that. Didn't know. I don't know. All my multiples of 11 currently. So the impedance, I'm going to split this up into different fractions. Okay. 968 over 121 plus 484 j over 121. Okay. And that first fraction does reduce. Okay. So 968 over 121 is 8. This whole thing reduces to 8. That's interesting. Okay. And then plus, now I don't think this does though, because 484 is like 22. Wait a minute. It sure does. It sure does. Yes, it does too. It's 4. And then I keep the j, which is square root of -1. Woo! Yeah, okay, that reduced a lot more than I thought it was going to. Okay. So there's your impedance. And this would be in ohms. Okay. I'm going to double check the teacher's guide and make sure that that is for sure the correct answer, because that came out nicer numbers than I thought. What was that 46? That was 46A. So let me check. H154, 46. Yeah, that's exactly what the teacher's guide is saying. 8 plus 4J ohms. That's it. All right, so I think pretty well covered that. That is a wrap on 3-3.